let's take a look at this topic here. So far, we've been looking at vectors in the context of, introducing a 3D space. And we've been looking at some of the properties that you've learned from extension 1. So things like the dot product, things like addition, and things like that. Now we're going to start to venture in towards things where you might not have seen as much. Now, vectors in geometry is a whole topic that actually you don't really look at since maybe like year 9 and 10, right? Because geometry they actually took out of these kind of courses, and there might be a hint of it in extension 1, but really in the focus for extension 2, because you guys are focusing a lot more on proofs and things like that, this is sort of a big focus as well, and we can show you some questions from the HSC that they'll look at. But let's just sort of get you thinking about geometry again, right? What do we remember from geometry, actually? Shapes. Shapes, yeah, okay. I'm thinking of biscuits, right? Pizza flavored shapes, that's the favorite flavor. We're dealing with shapes here, right? Not of the biscuit variety. What do we do with these shapes, Hudson?
Well, we certainly play around with them.
Play around with them. We can maybe like rearrange them, manipulate them. If you remember, a big focus in your geometry topics was actually looking at creating these proofs where you would prove things are... Yeah, great, good. Yeah, that's it. Congruency, similarity. This was a big focus of the topic back in the day, okay? And that's the kind of lens you want to take with these topics. It's a lot about looking at, can you prove certain things, or can you show certain things? It's less about, can you calculate, an answer like you would, or can you, perform sort of operation like you would in, your calculus topics, right? So that's the kind of lens you need to take this from. Now, show questions are always really tricky, I've found, because with show questions, you almost always have the answer. It's just how you get about that. And so the thing I want you to consider with these questions here is, okay, I want to make it clearly as possible shown to the marker that I know how to get the result. I'm not just using the result that they've given me and just sort of making my own way to the answer, right? I actually know what's going on, right? So let me show you a few questions just to get you started. And we'll often have to use the knowledge that we've learned so far about 3D vectors, right? So here's an example. Okay, so let's think about this, right? So when we're looking at our properties, we know that vectors, and typically, I want to just make a disclaimer here. With these geometry proofs, a large part of them will be in a sort of 2D space. Because like I said, it's very hard to visualize things in a 3D kind of space. Even just drawing them and trying to represent them is quite difficult, right? You can plot a point here and draw a vector out to this point, if that was you, for example. But the whole idea here is that we're not necessarily thinking about what they actually look like visually. We're just thinking about the properties. And it's kind of contrary to what I would usually say, especially with something like geometry. You want to visualize it, you want to sort of draw it, but sometimes it's quite difficult actually, especially with this kind of representation. So sometimes they will give you a diagram, other times they might not, just sort of be aware of that. But how do we know when vectors are parallel? Gradient's the same, okay, right? So you're thinking about maybe if they are the same gradient like this or something like that, right? That's something that it might look like. What would the gradient equivalent be? Or how could you show that in this situation though, right? Because there's no rise over run formula, so to speak, in a 3D context here.
You just figure out like them individually, so you figure out like, if you take away one on the axis and you just find like 2 of them, and then you do the other 2. Well, there's only 3, but like, if you do, say you do the X and Y first, and then you do like the Z and the X next, and then you get like, find out if those 2 are the same.
Okay, do you want to try that out? Any other ideas while Jordan's going to try that out for me? Any other thoughts on when are 2 vectors parallel? I mean, if you're thinking about it in 3D space, it's not necessarily clear. Just think about it in a 2D space. How do we know, for example, if I had A here and I had another vector B, how could I show that these 2 are parallel?
I mean, could you do projection? Because the projection of A would just equal A.
What would the projection of A? Oh, it would equal to A? Yeah, you can try the projection. Have we done projection in 3D vectors, by the way?
No, but I mean...
We haven't, but you could use the same formula. Because if you know the formula in the 2D space, it's the same formula in 3D space because it involves dot products and magnitudes, yeah. So do you want to try that for me, Hudson? Yeah? And Josh and Tom, are we going to find a third way to do this? Because while these boys are doing it, I'll just give you a hint. There is an easy way to consider
I knew
this.
it. The moment you told me to do it alone, I'm like, oh man, he's off. Then you told me to do it alone, I'm like, oh.
You're not off, you're not off. And this is what I always emphasize. There's always different ways. Everyone always thinks differently. And I don't mind which way you think. I want you to do what's natural to you. So you go ahead and do your projections.
Mate, this is natural. I'm just guessing.
Do you remember the projection formula? I can write it down if you...
Oh, it's A, B...
Or do you remember the projection formula?
Dot product of A and B on modulus of B squared times B.
Or the modulus of B squared
I forgot everything after B.
times the...
Times the vector of B.
Okay. Here's my projection formula for you, Hudson. So you're saying that this projection, A onto B, what should that equal to? It should just equal to A, you reckon. All right, let's find out. Okay.
Times the vector u by a scalar of 2, and that would equal to the vector v.
So Josh is saying if I multiply one of the vectors, you're doing your projections?
Yeah, I'm just thinking about...
Right out the projections. All right, so Josh is saying this. If I take this vector and I can multiply by a scalar to get to the other result, that's one way of showing that they're parallel. So think about something like this. If this was, I know, for example, I know this is 1.5 times A. If I know that B is equal to 1.5 the length of A, the only thing that's changed is its magnitude. The direction hasn't changed at all, or as Jordan was saying, the gradient, right? And so that's one method that we can do, which is quite approachable. We can just say that U is equal to, or would you want to do U or V? Which one would you rather do to show?
Do U is 1 over 2 times V, or V is 2
Yeah, it might be easier almost to think about V here, because if you start with V, you don't have to do any manipulation, right? You could just say V is equal to this, so in your component form. Remember, these are your coordinates. And then if you want to manipulate in such a way, well, we could, what could you do next?
divide everything by 2.
Yeah, you divide everything by 2, or you could even factorize it out. Because then what's this guy going to be? This is just
2 times U.
2 times U, perfect, right? So therefore, just write a little statement, especially with these sort of geometry type questions, you want to write a little concluding statement. Since they are scalar multiples of each other, they're parallel. Okay. How'd you go, Jordan, with your one?
I mean, I got them as the same thing or whatever, but like, I don't know if you get marks or like here.
Yeah.
Just go like,
What did you actually write down, by the way?
I just wrote down like, if you look at it, well, I just wrote down like U dash, well, U little m, so like the gradient of U in X and Y. So, I don't know how you want to write that, but I wrote that as 3 over 2, so that's just the rise over run. And then I did under that V over M is just equal to, or Vm, like xy is 6 over 4, so that's the same. And then if you take it in terms of zx, it's just negative 2 over 2 for the um1 again. That's the same. I don't know, it makes sense to me. Like, if I look at like a 3D line from this way, then you take out one of its directions, so then it's like it's got the same gradient that way. And then if you look at it from another angle, and it has the same gradient that way.
How do you feel about Jordan's method here?
I feel like you're not getting marked. I just learned that way, it's all good.
What do you think?
I get what he means. It's like you look from each plane and take the gradient at each plane.
Yeah.
and then if they're all the same, it's at the same sort of like angle.
I think what it comes down to is this, Jordan, like what makes sense can often sort of help you understand what's going on, but it may not necessarily be an acceptable form of a proof, so to speak, because like, what is the gradient of a vector? Like, do we have that concept that sort of exists in this sort of topic, right? We haven't really properly defined it. And so I think there's a lot of things that you could do which might sort of get you a result. But I would just sort of be careful to make sure you're using stuff that you've sort of been taught as well. And it sort of remains true for things that are like outside the syllabus, for example. Like there are things that are mathematically correct that you could use. For example, there's like a concept in vectors called the cross product, which we don't talk about, which is a perfectly mathematically valid idea. And that can actually be better at solving problems. But I'd just be careful using stuff like that because, you don't know who's going to be marking this. You don't know what they're expecting. So I sort of understand, as Alyssa was saying, I understand what you're saying. But yeah, can you understand how this would be another method you could use? Yeah. Right? Like you're kind of saying similar things with this, but this is just written a bit more succinctly, yeah? How's my projection looking?
I decided to go for the angle and theta 0. And if theta 0 means they're parallel.
Ah, okay, wait, so did you actually find the projection? Or what did you get up to? Or you think of...
Oh no, so I just did the other one, so like dot product of A and B over magnitude of A, magnitude of B, equals cos theta.
Oh, so you use the angle between the two vectors. Okay, so...
I'll be honest, I stole it from Tom.
Oh, so Tom's getting the credit for this one. Tom, you talk me through it then. What did you do?
Because dot product of U and B.
Yep.
The magnitude of A times magnitude of B.
Okay. And so what was my dot product? The dot product we got was... Well, remember, you would just multiply these and then add them together?
Equals 34.
2 times 4 plus 3 times 6 plus negative 2 times negative 4. And you said it's equal to 34. Okay? And then my magnitudes respectively, that's just Pythagoras' theorem, isn't it? So the square root of these individual parts. And what was that one?
17.
17. Square root of 17. And for B? How much?
Square root of 68.
Square root of 68. And then let's finish it off. I'll just run out of room, so I'm going to sneak it over here. So cos theta. And what were we expecting, by the way?
It to be 1.
So it's be...
Yeah, cos theta to be 1, so the angle between is 1.
Okay, so cos theta, let's have a look. So we've got here 34 over root 17 times root 68.
Yeah, and root 17 times root 68 is equal to 34.
Okay, perfect. And so theta, as you said, is equal to...
0.
And so can you see what's going on here, right? What's the angle between two vectors that are parallel? Well, essentially, because vectors can be moved around the plane, if you put them on top of each other, not only does this mean that they are parallel, actually if it's 0, there's another implication here. It means that they're in the same direction, right? They can also be parallel if they are in the opposite direction. What would the angle then be between? Yeah, you could write pi, that kind of thing. So it depends sort of what kind of situation you're creating here, right? Can you jot both of these down? Which one did you like better, by the way? Which method?
I mean, when I look at that multi-product,
Yeah.
scalar multiples,
Mm-hmm.
like, I mean, there's no way it's always going to be that. At one point, you'll just have to, like, start pulling out, like, the wildest numbers to go, oh, no, maybe it's a multiple.
Exactly, yeah. So it won't always be as obvious as is given here. And that's why I think it's always important to understand multiple different methods, whether it's this method, whether it's finding the angles, whether it's maybe even projections, right? You want to have a few ideas going on here. Can you jot these down for me?